Alright, silly people, here's the situation. We're going to be creating a code which calculates the heat capacity of a solid of temperature T using this equation here, which involves an integral. And we're going to have to evaluate said integral using Gaussian quadrature, which is, I think, like one of the last, well, certainly the last integration method that was covered before this problem. But I don't think it was covered very well, if I'm honest. But we're going to do it anyway by first of all noticing that we have exponent in the integrand, so I'm going to go ahead and import numpy as np, numpy as np. As always, we define the integrand to be a function f of x, and then we're just going to have it return the integrand, which is going to be x to the 4 times numpy exp to the x, and then it's actually also divided by numpy exp of x minus 1 squared, right? That's all fine and dandy. To do Gaussian quadrature, I'm going to do it the way that he does it in the book, and I'm going to wrap it up in a function called cv of t as suggested. To do the method that he uses in the book, he pretty much needs you to go in and grab the online resources Python function which does Gaussian quadrature, which is this, which I just pasted down. And whenever he does his Python codes, he tends to import everything explicitly instead of just importing all of NumPy and calling it when you need to. But I think just by putting some NP dots in certain places and making sure to import NumPy at the start, it should fix it just fine. So yeah, that's the Gaussian quadrature function that he uses in the book. And then first, before we start doing that, let's define some physical constants. So we need V, which is going to be 1,000 cubic centimeters. I have on good authority that in meters, that's just given by 1 e to the minus 3, right? Meters cubed. We need the rho, which is the number density, which is 6.022 e to the 28. Let's just store that in a variable called rho. We need Boltzmann's constant, which I'm going to call kb, and that's just 0.381 e to the minus 23. And then we need theta d, which is something that is also a constant for this problem. So theta d is going to be 428 Kelvin, right? Now we can say that we're going to do Gaussian quadrature with 50 steps. So n equals 50, where we have a starting point a equals 0, and b equals theta d divided by t. And then this is just now the shell of the Gaussian quadrature code that's in the textbook. So you calculate the sample points and the weights. So that's done by saying x comma w is equal to Gauss x, it's Gauss xw of n, according to the way the thing is defined. And then you map them to the required integration domain. So you say xp equals 0.5 times b minus a times x. That's plus 0.5 times, in parentheses, b plus a. And then you do wp equals 0.5 times b minus a times w. Right. I'm not getting into the theory here. I'm just kind of, again, just copying down from the textbook. So for k in range n, you would go through this for loop, and then you add onto your integral sum the value wp indexed k times f xp indexed k. Right. Then at the end, we'll have our function return the value of the integral, but also times all of the physical constants that we wrote down at the start. So it's times 9 times v times kb times rho times, and then in parentheses, we're going to put the t over theta d cubed. And I think that's even it. Yeah, this should be fine. I will say, the way that this code is written is not safe for arrays, so you can't just pass a whole array through the function and get it to work. So instead of doing that, to get the nice plot, which is the next part of the problem, we're going to create the t list to run over. So we're going to do numpy space just 5 to 500 with 1,000 steps for that nice high fidelity, and then we just go through another list that is going to be the CV list, so heat capacity list. For T in T list, we just calculate the heat capacity and append it to the list. Nice and simple that. And then we can plot it. And I just realized we should probably import matplotlib.pyplot as plt, and then just use the plot function for that. That's going to be T list versus CV list. See how it looks. Yeah, that's sort of the general shape of the heat capacity curve, so that is fine.